Hello, let's continue with our next chapter and our first section, 4.1, Combining Functions and Function Composition. Our objectives will be combining functions, difference quotient, and function composition. Difference quotient is probably the hardest thing here in this section, but if you're interested in going on or need to get to calculus, then it's something that you will see again in the future. So it'd be great if you learn it well while you're here at college algebra. Combining functions. Starting already with arithmetic, most every topic of discussion in mathematics includes the four operations of addition, subtraction, multiplication, and division. Functions are no different, and we start this chapter with these 4 ways of combining functions. Given any two functions, say f of x and g of x, the following combinations are defined as follows. So first we have the sum, and in a sense, this is our shorthand. And what this means is we're going to take each function separately and add them together. We also have our difference, which is just subtraction, and same idea. Essentially, this is our shorthand that we're taking function f and subtracting function g. And what we're doing is taking function f of x, writing a subtraction sign, and then writing your function g of x, whatever it may be. We also have product, which is multiplication. We can multiply any two functions, and this would be our shorthand, f comma fg close comma, parentheses, and then parentheses x close parentheses. And what this means, we're taking our function f of x, we're multiplying by our function g of x. And division is no different. We have some type of shorthand, and then we're dividing our function on top and dividing it by our function in the bottom. And that would be our quotient, or division. So let's see an example. Example 1, considering the function f of x equals 3x minus 7 and g of x equals x squared plus 2x, find f plus g of negative 2, f minus g of 4, f times g of 3, and f divided by g of negative 5. So we were given two functions. Each one has its own name. We have f of x, which is 3x minus 7, and we're also given g of x, which is x squared plus 2x. And we're going to follow each rule that we're asked to do. So we first have f of g plus, f plus g of 2. So we're going to take our function f and input a negative 2, and then we're going to add it to our function g and input a negative 2. So let's add a bit more work to our notes. So here we have our function f. Now if we want f of negative 2, this means for every x we're going to plug in a 2. So we have 3 times negative 2 minus 7. 3 times negative 2 is negative 6. Minus 7, we get negative 13. So we now say that f of negative 2 is equal to negative 13. So what we're saying is that these two things are equal to each other, and we'll use them interchangeably. Now we can do g. For g of x, we have x squared plus 2x. For every x, we're going to plug in what it's asking, which is a negative 2. So we find g of negative 2, we plug in a negative 2, we get negative 2 squared plus 2 times negative 2. All right, negative 2 squared gives me positive 4, and then negative 2 times that positive 2 gives me negative 4. So I have 4 minus 4, we get 0. So g of negative 2 equals 0. And again, I can use g of negative 2 and 0 interchangeably. All right, so back to our problem. We have f plus g of negative 2. So this means f of negative 2 and g of negative 2. We said that f of negative 2 is equal to negative 13. So replace it with a negative 13. And g of negative 2 is equal to 0. So we'll change that with the 0. So that we get negative 13 as our answer. Now for b, we have f minus g of 4. And so that's asking to find two things separately. Find f of 4 and then find g of 4. So we do f of 4. That's going to take our function f, and for every x, it's telling us to plug in a 4. So we have 3 times 4 minus 7. That gives us 12 minus 7, which is 5. So f of 4 is equal to 5. Now g of 4, we're going to plug in a 4 for every x, like we have above. So we have 4 squared plus 2 times 4. 4 squared is 16, plus 8, we get 24. So let's go ahead and fill our answers. F of 4 gives us 5, and G of 4 gives us 24. So 5 minus 24, answer is negative 19. Alright, I trust you can do the rest from here. I'm pretty much out of space, so I'll leave those up to you. In this first example, the combination of the two functions included the evaluation of each function at a specific value. The next two examples show the general combinations of two functions. So let's go ahead and do this next example. It reads, considering the functions f of x equals 3x minus 7 and g of x equals x squared plus 2. Find f plus g of x, f minus g of x, f times g of x, and f divided by g of x. So the difference here that makes it different from example 1 is there's no numbers. All we can do is just write as is and combine like terms. I can't spell. Combine like terms whenever possible. And that's all you can do. So take a look. For example, we have f of x and g of x. We have f of x, which is 3x minus 7. And we have g of x, which is x squared plus 2x. And all we can really do is write a plus in between. All right, and we combine like terms from there. I see that I have an x and an x, so I can combine those to get 5x. And that's pretty much it. And from here, all I can do is make sure I write it in standard form. Meaning highest degree to lowest degree. All right, going on to B. Similar to A, all we're doing is taking each one and writing a sign in between. So we have our function f, which is 3x minus 7. And we have our function g, which is x squared plus 2x. And all we did was write a minus in between. And from there, all we can do is combine like terms. My like terms are the 3x and that 2x. So 3x minus 2x gives me 1x. And so this is our answer. Notice that they're different because we're applying a different sign to our second function. When multiplying, this should have been a multiplication. All we can do is multiply if possible. Sometimes we won't be able to multiply, and all we can do is just write the question as is. So here we have this problem, and we can distribute. 3x times x squared gives me 3x cubed. 3x times 2x gives me 6x squared. Negative 7 times x squared, negative 7 squared. Negative 7 times 2x gives me minus 14x. And from there, we combine like terms. And so we get this as an answer. For D, f divided by g, all we can really do is write one on top of the other and simplify whenever possible. Usually, it's some type of factoring technique that comes into handy, but for this problem, we see there isn't much I can do. I mean, yes, I can factor my denominator, but it won't help me simplify any further. So this is our answer. Knowing that each combination of two functions creates a new function, we often discuss the topic of domain when considering f plus g of x, f minus g of x, f times g of x, and f divided by g of x. For f plus g of x, f minus g of x, and f times g of x, the combination of two functions involving addition, subtraction, and multiplication, the domain will be the intersection of all domains of f and g. So whatever they have in common. I highly suggest you take the time to, if you're being asked for the domain, draw a number line and then see what f is, what the domain is, and what the domain is for g or whatever your function is labeled, and look for any type of overlapping value. So that's what I suggest for those two. Moving forward, for f divided by g, the domain will be the intersection of the domains along, so very important, along with any excluding values which make your denominator equal to 0. So let's see g of x equal to 0 because g is in the bottom. But really, it's the denominator value that plays a large part in this. Example 2 again. Considering the functions f of x and g of x, find the domain using those four operations. The domain of f is all real numbers because if we take a look at f, we're just plugging in a value for x. So when you think of domain, think of what can x be? And usually our only restriction values are when I have a denominator, when I have a square root, and in the future we'll talk about other values like logarithms. But for the most part, division values and square roots are our biggest problem. So for f, we see that x can be any number. For g, x can be any number. So our domain is all real numbers for f and g. The intersection, so what they have in common for all real numbers and all real numbers is all real numbers. So if we were to draw a number line for f, everything is part of my answer, right? And for g, the whole number line is also part of my answer. So then when I'm asked to work with the addition or the subtraction or the multiplication, I will also get all real numbers, negative infinity to infinity. But what about the division problem? F over g of x. The domain is all real numbers except our domain. Whatever our domain gives us a problem. So remember, the problem is it can never be 0 in the denominator. That makes it undefined. So we need to find out what values make your denominator 0, which is x squared plus 2x. We need to solve for it. If we solve, we can factor. And we can set our factors equal to 0 by the zero product property. And we get that our answer is x equals 0 and x equals negative 2. Subtract 2, which we have here. So therefore, our domain is all real numbers except negative 2 or 0. So if we draw this on a number line, And you don't have to draw a number line. I just find it super helpful. All right, so for our function f, we said all real numbers. So it's all the numbers there. And for my function g, let me pick another color. For my function g, we have holes. We have holes at 0 and at -2. So we have 0 and -2. Those are going to be holes in our answer. But everything else is still our answer. So all numbers except -2 and 0. So where do they overlap? We see the overlap from -infinity up to -2. -2 has an open circle, so therefore it has a parentheses. It continues on from -2 to 0, parentheses because it's an open circle, and then from 0 on to infinity. Because we have a break, we write unions. So this is our answer here. Example 3. Considering the function p of x equals x plus 3 and q of x equals square root of x plus 4, find each of the following and state the domain. Okay, so let's take a look at each one separately. For p of x, do we have square roots or fractions? No, right? So for that one, our domain is all real numbers. If you don't want to write all that, all real numbers, shorthand is an R with an extra stick right there. All right, for Q, what can X be? We have a square root. And remember, I can't take the square root of a negative number. That's a problem. So I need to find out what makes it negative. To do so, we take our value inside, x plus 4, and we want all numbers that are greater than 0, but they can also be equal to 0. I can take the square root of 0, that's just 0. So we can solve for that. We move the 4 over, and we're left with x is greater or equal to -4. So this means I can use all values that are greater than 4, including 4. So it would be from -4 to infinity. 4 is included, so it has a bracket. That's our domain for Q. All right. So if I'm subtracting, like A is asking for, P minus Q, we write each one separately, but with a minus in between. Now for this one, you see, I can't combine them, right? I could just write a minus in between, and that's okay. All right, so we set up that our domain for P is all real numbers. Our domain for Q is 4 to infinity. So where do they overlap? This one's pretty easy to see. One of them is everything, and our only problem that we must consider is from -4 and on. And -4 is included. So where do they overlap? We see that they only overlap in these values here. So because of that, our answer would be -4 to infinity. What did I do? All right, let's go ahead and continue. All right, for B, we see that Q of P, we have a division, and we have two restrictions. I have to consider the domain of Q, but I have to make sure our denominator doesn't create a 0. And if it does, we need to find out where. So x minus 3 equal to 0. We add 3 to both sides. We get that x is equal to 3. So that's another domain I have to consider. The intersection of domains for P and Q is -4 to infinity. We must also include where our denominator equals 0, namely x equals 3. Therefore, our answer is -4 to 3 and 3 to infinity. How does that happen? Let's draw on a number line. That really helps get things straightened out. So we see that it goes from -4 to infinity with a closed circle. And our denominator says it can be anything except positive 3. So 3 is the open circle. So where do they overlap? We see they overlap from negative 4, and then we have to stop at 3. 3 has an open circle, and then we continue from 3 to open infinity. And that's our answer here. We continue our discussion of combining functions with the introduction of difference quotient, a topic that will become very significant in calculus. Considering the continuous section of the graph of the function f of x containing 2 points and a single arbitrary f of x and the second point f plus h, f of x plus h. So we have this here. This would be like a point x comma y, and this is something more. So x plus something else, so let's make it a 2, and y 2, similar to slope. Think of this as a slope actually. So our difference quotient is finding the distance between these two x values at some value h. So we're saying that this can be for any arbitrary h that's more than this point. So it goes from one point to the other. Knowing that the slope of a line can be defined as m equals y2 minus y1 over x2 minus x1, we calculate the slope of the line through using our new points. And if we do, once we simplify it, we're left with this formula. This formula here is your difference quotient. And if what I said above and that all the writing made no sense, it's okay. This is all we want. We want that formula. So how do we find the difference quotient of this problem? Say example 4. Find the difference quotient of f of x equals 4x plus 5. All right, so we have our formula. We have f plus x of h, that's one part, and then we have another part, f of x. And we have to find those two pieces. I recommend you find them separately. Find f of x plus h, and then you have f of x that's given. But label them separately and then put them together. All right, so we have f of x, which is just our formula, which we said from our problem is 4x plus 5. Now all we're going to do is for every x in our function, we're going to write an x plus h in parentheses. We do so here, so all we have to do is distribute that 4. So we have 4x plus 4h plus 5. Now let's put them together according to our formula. We have f of x is 4x plus 5, and we have f of x plus h, which is 4x plus 4h minus 5. So our function asks for f of x plus h, which is that there. And then our function asks for minus f of x, which we have here. We have set it up. All we have to do is write a minus in between and write the h in the bottom. Okay, from there we simplify. Usually involves distributing that negative. So from there we combine like terms. Usually what you'll see is that stuff cancels out to make 0. So we see that 4x minus 4x is 0, 5 minus 5 is 0, and we're just left with 4h over h. Usually this h's will end up dividing to make 1, so we're left with something else. But your h's usually, you have some factoring to do and get a simplified answer. Example 5 is more tricky. I'll leave this for you to try. The fifth and final operation by which we combine a function is called function composition. Given any two functions f of x and g of x, the composition of f of x and g of x is denoted as f composition of x. No, it's not fog, but it looks like fog. So if it helps you remember, you can say that. And that just means we're going to take a function and plug it into the one before. Think of it as maybe like nesting dolls, like those Russian nesting dolls, where one doll goes into another doll, into another doll. So let's do example 6. We have function f of x is 3x minus 7, and g of x is x squared plus 2x. Find the following. F composed of g of negative 4. All right, so what we're going to do is we're first going to find f of g of 4. G of negative 4. Because we see here, this is what it defines that. We work from the inside first. So g of negative 4 gives you negative 4 squared plus 2 times negative 4. That was a 4. So we get 16 minus 8, which gives us 8. So g of negative 4 equals 8. Now remember the equals, so I can use them interchangeably. So do you see how we have g of negative 4? Let's replace that with our answer, which is 8. Now I have to work from the outside. F of 8. Our function f, which we have here, we input an 8, so we have 3 times 8 minus 7. So we get 24 minus 7, which is 17. And that's our final answer. B, C, and D are similar. Let's move on to example 7. The composition of functions in example 6 requires the evaluation from the inside function first. Super important. Then using that value and evaluating the function outside the function. In general, the same process is used to find the composition of functions when there is no specific evaluation involved. So next, there's no numbers. And all we're going to do is write a function within another function. So let's take a look at A, f composed of g of x. So we have our function f, and we have our function g. And the first one wants f composed of g of x. You write your formula. So this is how it's written as a formula. You write the outside, and then the inside you put the second one. In this case, g. So this is saying in your function f, we're going to plug in for every x, your entire function g. So for that one little x, I'm going to write this whole thing of x squared plus 2x. All right, so we write it as f of x squared plus 2x, and we plug it in for that 1x, and you simplify. In this case, it involves us distributing. So we have 3x squared plus 6x minus 7. Now notice that for b, it's switched order. G composed of f of x. So we write it as our formula, g, and for every x and g, I'm going to plug in f of x. So if you want to, you can take your pencil and give yourself a little image of what you're going to do. So in your function g, you're going to plug in your function f of x. And we do this for every x. So if we have multiple x's, we have to repeat the process. So for every x in g, I'm going to write f of x. And what is f of x? 3x minus 7. All right, so we have x squared, which is 3x minus 7 squared, plus 2 times x, and x will now be f, which is 3x minus 7. We simplify, so here I have to FOIL. So if it's squared, remember that's 3x. That's 3x minus 7 times 3x minus 7, and you have to do the work of multiplying that out. That's how they got this here. And then they distribute the 2, so we have 6x minus 14. We combine like terms, and we get this answer here. Remember to combine like terms. We can even do something like C, f composed of f. So this means, let me try to guide you here. For my function f, for every x, I'm going to plug in the whole thing, 3x minus 7. So my function f, I'm going to put in 3x plus 7 for every x. So we just have the x there. We distribute the 3, and we combine like terms. So there's our answer there. This is a topic that I usually see students struggle with. And I know I'm going very quick, but it's a video, so I'm hoping if something didn't make sense, you'll pause it, rewind, watch it again. So make sure you understand this because this is something I know might be a bit of a hiccup. In the next example, we'll include discussions of domain as we did for composition of two functions. Example 8, considering the function p of x equals 2x plus 5 and q of x equals square root of x minus 3, find the following and determine the domain. So I'll do A with you. P of q of x equals, so by formula, we write the one second inside, right? So what this says is we're going to take our function q, and we're going to plug it in for every x. All right, so we have 2 times x, but instead of x, I'm going to write q, which is square root of x minus 3. I can't do anything there. I just rewrite it. What is our domain? Our domain is the two functions. So we have x plus 3 or square root of, or 3 to infinity. All right, I'll leave the rest for you to try. It pretty much goes on the same value where we have to see where they both overlap and consider your new function because your new function also plays a new factor into this. All right, if you have any questions, please email me or post them in our discussion board. Thanks.